And now in this lecture we'll find out the radius of the small circle. In the drawing we have a big triangle, triangle ABC, big right triangle, triangle ABC, and we know that side AB equals to 6 units in its length, side AC equals to 8 units in its length. This is angle ABC, that is a right angle. Inside the right triangle ABC we have this small circle, we have also this big semicircle, and our mission is to find out the radius of this small circle. So first of all, we will define the relevant points to this question with letters. We will define the center of this small circle. This point is point P. Likewise, we will define the center of this big semicircle. This point is point Q. We define the point of tendency of tangent AB with this small circle. This point is point N. We define the point of tendency of tangent AC with this small circle. This point is point K. We will define the point of tendency of tangent AC with this big semicircle. This point is point H. And finally, we will define the touching point of this small circle with this big semicircle. This point is point L. So here we can implement the Pythagoras theorem on this right big triangle, triangle ABC. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABC is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. So I write it down. In the right triangle, triangle ABC, here by PT is the abbreviation for Pythagoras theorem. So AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total we should find out that AC square equals to 36 plus 64, that is 100. AC square equals to 100. We take a root out of this equation. Finally, we get that the missing hypotenuse AC is equals to the square of 100, that is 10. So AC equals to 10 units in its length. The hypotenuse AC equals to 10 units in its length. AC equals to 10. Here we can implement rule 2 in our drawing. I'll repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a current standpoint to a circle are equal. In the drawing we have a circle, and we have, this is the current standpoint, point P. From this current standpoint, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this current standpoint, point A, from this current standpoint, point A, we have two tangents to the big semicircle. We have tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. So write it down. according to rule 2, AB equals to AH. But AB equals to 6 according to what is given us in the question. So when I agree that AB equals to 6, and from this equation 6 equals to AB equals to AH, we will derive that AH is also equals to 6 units in its length. AH equals to 6. This 978 is equals to 6 units in its length. So let's see here that AH equals to 6 units in its length. What is the length of the missing line segment? Line segment is edge C. Edge C equals to AC, that is 10, minus AH, that is 6. So in total, edge C equals to 10 minus 6, that is 4. So edge C equals to 4 units in its length. In the next step, we join points Q and H together by a straight line. Point Q is the center of this big semicircle. Point H is the point of the big semicircle itself. So QH is the radius of this big semicircle. We will define the radius of this big semicircle as B, therefore QH equals to B. According to our definition. Here we can implement rule 1. So I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have tangent AB. This is tangent AB, that is tangent to this circle at point M. In addition, we have the radius of M. The radius of M is equal to R, is drawn to point M, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 1. So we can implement rule 1 in our drawing. Because in our drawing we have the radius QH that is equals to B, so the radius QH is drawn to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. By doing this construction, we can engineer the right triangle QHC. In the right triangle QHC, we have this angle C, that belongs to the right triangle HQC. But this angle C belongs not only to the right small triangle HQC, but it is also belongs, angle C also belongs to the right big triangle ABC. So we'll define the size of this common angle C as alpha. So in the right small triangle HQC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we focus on the right big triangle ABC. The right big triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. According to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that this right big triangle, triangle ABC, is similar to this small right triangle, triangle HQC. So I write it down. We will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle HQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABC, in the right big triangle ABC, and it is equal to this angle. This is actually angle QHC, in the small right triangle HCQ. So repeat again. Actually found out that angle ABC, the big right triangle ABC, equals to angle QHC in the small right triangle HCQ. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So I can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if you relate to this angle alpha as it is belongs to the big triangle, triangle ABC, it will be defined as angle ACB. And angle alpha equals to itself. So if we relate to angle alpha as it is belongs to the small right triangle QHC, it will be defined as angle HCQ. I'll put it again. Actually found out that angle. So this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle BAC in the big right triangle ABC, and it is equal to this angle, that is actually angle HQC in the small right triangle HCQ. Repeat again, I should found out that angle BAC, the big right triangle ABC, equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I can prove that all the triangles of this big right triangle ABC are correspondingly equal to all the triangles of this small right triangle HCQ. Therefore those two right triangles are similar to each other according to angle similarity rules. So I write it down. Actually found out that the big right triangle ABC is similar. This is the sign of similar to the small right triangle HCQ according to angle similarity rule. And from the fact that the big right triangle ABC is similar to the small right triangle HCQ, we will derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC, the big right triangle ABC, over side HC in the small right triangle HCQ. So I'll repeat again. We will derive that side AB, the big right triangle ABC, over side HQ in the small right triangle HCQ equals to side BC, the big right triangle ABC, over side HC in the small right triangle HCQ. AB is 6 over HQ. HQ is B. Is the radius of the big semicircle is equals to B. Equals to BC. BC is 8 over HC. HC is 4. So in conclusion, we shall find out that 6 over B equals to 8 over 4. 8 over 4 is 2. Therefore, 6 over B equals to 2. Here we multiply this equation by B and finally get that 6 equals to 2B. Here we divide this equation by 2 and finally get that the missing radius B of the big semicircle equals to 6 over 2, that is 3. The radius B of this big semicircle equals to 3 units in its length. Here, point Q is the center of this big semicircle, point B is the point of the big semicircle itself, therefore QB is the radius of this big semicircle is equal to 3. So I write it down. QB equals to 3 units in its length. This is the radius of the big semicircle. In the next step, we will join points P and N together by a straight line. Point P is the center of this small circle, point N is the point of the small circle itself, therefore Pn is the radius of this small circle. We define the radius of this small circle as A, therefore Pn equals to A. A is the radius that we are looking for in this question. Here we can implement all one in our drawing, one in our drawing. We have the radius Pn that is equals to A, the radius Pn is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, join points P and K together by straight line. PK is of course the radius of this small circle, is equals to A. The radius PK is drawn to point K, that is the point of tendency of tangent AC with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, all one. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle you will draw two tangents to that circle, then the angle that will be created between the two tangents, its angle bisector must pass through the center of the circle. So in the drawing we have a circle, and this point P, is a common external point in relation to this circle. From this common external point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we created this angle. Angle APB was created by drawing tangent PA and tangent PB to this circle. And according to rule 15, the angle bisector of this angle must pass through point O, that is the center of this circle. Again, the angle bisector of this angle must pass through point O, that is the center of this circle. So whenever you draw two tangents from a common external point towards a circle, you will create an angle, and the angle bisector of the angle as created by the two tangents must pass through the center of the circle. So we can actually implement rule 15 in our drawing. Why? Because in our drawing we focus on this common external point A. From this common external point A, we have two tangents to this small circle, tangent AN and tangent AK. By drawing the two tangents AN and AK, we can do this angle. Again, this angle A repeat again. Repeat again. This is angle A that was created by drawing the two tangents AN and AK to this small circle. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. Repeat again, the angle bisector of this angle A must pass through point P, that is the center of this small circle. So here, PA is the angle bisector of angle A, and it of course passes through point P, that is the center of this small circle. If we define the size of this angle A is 2 theta, then angle bisector PA bisect angle A into 2 halves. Each half must also be equal to theta, of course. This is the first half, and this is the second half of angle A, is equal also to theta. Okay. Again, according to rule 15, the angle bisector of this angle A must pass through point P. You can see here that angle bisector AP passes through point P. So in conclusion, you can actually write down that the angle bisector of angle A passes through point P. So write it down. We found out that according to rule 15, the angle bisector of angle A passes to point A. To point P, of course. And the angle bisector of angle A passes through point B, that is the center of this of the small circle. Repeat again. We can find out that the angle bisector of this angle A passes through point B, that is the center of this small circle. This is of course according to rule 15. Likewise, we will continue to focus on this common standpoint point A. From this common standpoint point A, we have two tangents to the big semicircle, tangent AB and tangent AH. Again, we have tangent AB and tangent AH. By drawing the two tangents AB and AH, we actually created the same angle A. Again, angle A was created by drawing tangent AB and tangent AB to this big semicircle. Now we can implement rule 15. Why? Because according to rule 15, the angle bisector of the same angle A must pass through point Q, that is the center of this big semicircle. Again, because of the fact that tangent AB and tangent AH created angle A, according to rule 15, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. So we draw the angle bisector QA, and of course the angle bisector of the same angle A passes through point Q, that is the center of this big semicircle. Again, angle bisector of this angle A passes through point Q, that is the center of this big semicircle. So I can write down actually that the angle bisector of the same angle, angle A, passes also through point Q, that is the center of the big semicircle. And finally, it is very clear that the angle bisector of this angle A passes also from point A. So I write it down. The angle bisector of angle A passes also through point A. In conclusion, we found out that the angle bisector of this angle A passes through points A, P and Q. So I write it down. The angle bisector of angle A passes through points A, P, and Q. Repeat again, I should found out that the angle bisector of this angle A passes for points A, P, and Q. It passes for points P and Q according to rule 15, and it also must pass for point A. It is very clear that the angle bisector of angle A must pass for point A. But the angle bisector of angle A is a straight line. Okay, you can see that AP, the angle bisector of angle A is a straight line, and AQ, the angle bisector of the same angle A, is also a straight line. Actually, the angle bisector of any angle is a straight line, and especially the angle bisector of angle A must be a straight line. So if you know, we should find out that the angle bisector of angle A is a straight line. But all the 3 points A, P, and Q are located on the angle bisector of A. Therefore, all the 3 points A, P, and Q are located on the same straight line. So I write it down. We actually found out that all the 3 points A, P, and Q are located on the same straight line. And the straight line is of course the angle bisector of angle A. Again, the straight line is the angle bisector of angle A. So if you know, okay, the straight line is the angle bisector of angle A. So I found out that points A, P, and Q are located on the same straight line, or line segment APQ is one straight line. Again, line segment APQ is one straight line. So if you know, line segment APQ is one straight line. If line segment APQ is one straight line, it means that angle theta is a common angle that belongs both to the small right triangle A and P, and angle theta belongs also to the big right triangle BAQ. So right now I should have found out in conclusion that angle theta is a common angle that belongs to both triangles. because of the fact that 90 degree APQ is 1 straight line, it means that angle theta is a common angle that belongs to triangle, the small triangle A and P, and also to triangle ABQ. Then again, angle theta belongs to the small right triangle AP, and angle theta belongs also to the right big triangle, triangle ABQ. In the next step, we will focus on the big right triangle, triangle ABQ. The big right triangle, triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees. Again, 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in a triangle. Likewise, according to the symbol in triangle A and P, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. In the next step, we will prove that the big right triangle, triangle ABQ, is similar to the small right triangle, triangle ANP. So I write it down. So why the big right triangle ABQ is similar to the small right triangle, triangle ANP? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABQ, in the right big triangle ABQ, and it is equal to this angle, this is actually angle ANP, and the small right triangle APN. So repeat again, if we found out that angle ABQ in the big right triangle ABQ equals to angle ANP in the small right triangle APN, they are both equal to 90 degrees, therefore they are equal to each other. In addition, In addition, this is the common angle theta that belongs to both triangles. So you can write down that angle theta equals to itself. It's a common angle that belongs to both triangles. So if we relate to this angle theta as it belongs to the right big triangle ABQ, it will be defined as angle BAQ. And angle theta equals to itself. So if you relate to angle theta as it belongs to the small right triangle ANP, it will be defined as angle NAP. So this equation means that angle theta equals to itself. We just call to angle theta two different names. And finally, those two angles they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle AQB in the big right triangle ABQ. And it equals to this angle, it's actually angle APN, and the small right triangle ANP. So again, if we found out that angle AQB in the big right triangle ABQ equals to angle APN in the small right triangle ANP, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So if we prove that all the triangles in the big right triangle ABQ are correspondingly equal to all the triangles in the small right triangle ANP, therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. So actually found out that the right big triangle ABQ is similar, this is the sign of similar, to the right small triangle ANP according to angle similarity rule. And from the fact that the right big triangle ABQ is similar to the right small triangle ANP, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again, we will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP, the small right triangle ANP. AB is 6 over AN. AN is the missing side, so we will leave it as it is. And it is equals to BQ. BQ is 3. It's actually the radius of the big semicircle. It equals to 3 units in its length. Over NP. NP is A, it is the radius of this small circle, that is the radius that we are looking for in this question. So NP is A. So in conclusion, we found out that six over an equals to 3 over a. Here we cross multiply this equation. And we get that six a equals to 3 times an. So here we divide this equation by 3 and we get that finally that the missing side an is equals to 2a. So we actually found out that this missing side an equals to 2a units in its length. So I write it down here. A equals to 2a units in its length. We know that AB equals to 6 units in its length, AN equals to 2A, so the missing 9/7 NB, this is the missing side 9/7 NB, it will be equal to AB, that is 6, minus AN, that is 2. So in total, NB equals to 6 minus 2A. So I write it down. The length of this missing 9/7 NB is equals to 6 minus 2A units in its length. In the next step, we will do a construction, that is to say from point P, we will draw perpendicular on BQ. Again, from point P, we will draw perpendicular on BQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we created the quadrilateral NPBZ. Inside quadrilateral NPBZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBZ we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral NPBZ as a rectangle because it has 4 right angles. So write it down, quadrilateral NP, this quadrilateral NPBZ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPBZ, side NP must be equal to the opposite side BZ, but NP equals to A, therefore BZ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPBZ, side NB must be equal to the opposite side PZ. But NB equals to 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. So write it down, PZ equals to 6 minus 2A units in its length. In the domain, we have an external notch between the small circle and the big semicircle. That is to say, they are touching each other externally at this point L. Whenever you have an external notch between two circles, you can implement rule 10. I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching points. So in the drawing we have two circles. Those two circles have an external notch between them at point P. That is to say that touch each other externally at this point P. The center of this small circle is here at point M. The center of this big semicircle is here at point O. And the straight line that connects the centers together is of course the straight line MO. And this straight line MO, according to this rule 10, must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. Again, according to rule 10, MPO, this rule 10, MPO is one straight line. So, we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and this big semicircle. That is to say, they touch each other externally at point N. Therefore, we can implement a rule 10. The center of this small circle is at point P. The center of this big semicircle is here at point Q. And the straight line that connects the centers together is the straight line PQ, of course. According to rule 10, the straight line PQ must pass through point L, that is their touching point. Again, the straight line PQ must pass through point L, that is their touching point. Or PLQ is one straight line. Again, according to rule 10, PLQ is one straight line. If PLQ is one straight line, it means that PQ is also a straight line. But what is the length of the straight line PQ? PQ equals to PL plus LQ. So I write it down. PQ equals to PL plus LQ. Only because of the fact that PLQ is one straight line, PQ equals to PL plus LQ. It is not trivial that PQ equals to PL plus LQ, but only because of the fact that PLQ is one straight line, PQ equals to PL plus LQ. So PQ equals to PL. PL is the radius of this small circle, that equals to A. A is the radius that we are looking for in this question, plus LQ. LQ is the radius of this big semicircle, and is equals to 3 units in its length. So in total, we actually found out that the length of line segment PQ equals to A plus 3. In the next step, I'll copy the right green triangle PZQ in a new page, and we'll implement the Pythagoras theorem of this right green triangle PZQ. PZ equals to 6 minus 2A, side ZQ equals to 3 minus, okay, so we'll find out the length of side ZQ. What is the length of side ZQ? From the drawing it is very easy to see that ZQ equals to BQ minus BZ. So ZQ equals to BQ, that is 3, minus BZ, that is A. So in total, ZQ equals to 3 minus A. And the length of the hypotenuse PQ of the right green triangle PZQ is A plus 3, or 3 plus A. Here by PT is a evaluation from Pythagoras theorem. So actually, this is again right triangle PZQ that the correct from the original drawing. According to the Pythagoras theorem, in this right triangle PQ square, that is the square of the hypotenuse, must be equal to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. So I write it down. I shall find out that PQ square, that is the square of the hypotenuse, is equals to PZ square plus ZQ square. PQ is 3 plus A, therefore PQ square is 3 plus A square, and it is equals to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square plus ZQ square. ZQ is 3 minus A, therefore ZQ square is 3 minus A square. So in conclusion, I found out that 3 plus A square equals to 6 minus 2A square plus 3 minus A square. We'll open the brackets on both sides of the equation, and we get that 3 plus A square equals to 3 square, that is 9, plus A square plus 2 times 3 times A, that is 6A. On the other side of the equation we have 6 minus 2A square. 6 minus 2A square equals to 6 squared, that is 36, plus 2A squared. 2A squared is 4A squared. Minus 2 times 6 is minus 12, and minus 12 times 2A is minus 24A. Plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared. Minus 2 times 3 times A is minus 6A. So here we have 9 on both sides of the equation, so 9 get cancelled. We have also A square on both sides of the equation, so A square also get cancelled. After we cancel those two expressions, in this side of the equation we left only with 6A. On the other side of the equation we have 36 plus 4A squared. And here we have minus 24A minus 6A is minus 30A. So in conclusion, I should found out that 6A equals to 36 plus 4A squared minus 30A. Here we subtract 6A from this equation and get that 6A minus 6A is 0 equals to 36 plus 4A squared, and 38 minus 6A is minus 36A. In conclusion, we found out that 0 equals to 36 plus 4A squared minus 36A. Here we divide this equation by 4, and we get that 4A squared A squared over 4 is A squared. Minus 36A over 4 is minus 9A. 36 over 4 is 9, and 0 over 4 is 0. In conclusion, I found out that A squared minus 9A plus 9 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is AX squared plus BX plus C equals to 0. In this general formula, A, B, and C are the coefficients of this quadratic equation, and X is the variable that we are looking for. And we will find out the value of X according to the following formula. X equals to minus B plus minus square root of B squared minus 4 times A times C over 2A. Now, specific quadratic equation, that is to say A squared minus 9A plus 9 equals to 0. The variable that we are looking for is A, therefore X equals to A. The coefficient A equals to 1, the coefficient B equals to minus 9, and finally the coefficient C equals to 9. The only thing that is left to do is to put the data of our specific quadratic equation inside this formula for X, and we find out the value of the values of A, because X equals to A. So X equals to A, so we have A equals to minus B. B is minus 9, therefore minus B is minus 9, that is plus 9. So equals to plus 9 plus minus square root of B squared. B is minus 9, therefore B squared is minus 9 squared, that is 81, minus 4 times A. A is 1, so minus 4 times 1 is minus 4 times C. C is 9, so minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 divided by 2A. A is 1, so 2 times 1 is 2. So we actually found out that A, that is the radius of the small circle, that is the radius that we are looking for in this question, is equals to 9 plus minus root of 81 minus 36 is 45 divided by 2. So here we have two solutions that are possible for A. The first solution for A is that A equals to 9 plus square root of 45 over 2. So according to the and this expression 9 plus square root of 5 over 2 is greater than 3. So according to the first solution for A, the radius A of this small circle is greater than 3 units, because this expression 9 plus square root of 45 over 2 is greater than 3. But it is impossible that the radius A of this small circle is greater than 3. Why? Because of the fact that the radius of the big semicircle equals to 3 units. And the big semicircle is definitely greater than the small circle, and therefore the radius of the big semicircle must be greater than the radius of the big semicircle that equals to 4 units must be greater than the radius of this small circle. In other words, the radius of this small circle must be less than 3 units. But according to the first solution, the radius of the small circle is greater than 3 units. So this answer is a correct answer. This solution is a correct solution. We cancel the solution, and we left only with the second solution that is possible for A. According to the second solution, the radius A of the small circle is equals to 9 minus square root of 45 over 2. So the radius A is equals to 9 minus square root of 45 is 9 times 5, so we substitute 45 by 9 times 5 divided by 2. So the radius A of the small circle equals to 9, and we have minus square root of 9 is 3, so inside the root we left only 5 divided by 2. So according to the second solution for A, the radius A of this small circle equals to either 9 minus 3 times square root of 5 over 2 units, so in terms of numbers it is equals to 1.146 units. That is less than the radius of this big semicircle is equals to 3. Okay, the radius of this small circle equals to either 9 minus 3 times 4 to 5 over 2 units in its length, or in terms of numbers, the radius of this small circle equals to 1.146 units in its length. In the next step, I will summarize the lecture. In this lecture, we found out the radius of this small circle. Okay, so in the drawing, we have the right triangle ABC. We know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. This is angle ABC, that is the right angle. Inside the right angle ABC, we have this small circle and this big semicircle. The small circle touches the big semicircle at point L. Again, our mission is to find out the radius of this small circle. In the first step, we defined the relevant points to this question with letters. We defined the center of this small circle, this point is point P. We defined the center of this big semicircle, this point is point Q. Likewise, we defined the point of tendency of tangent AB with this small circle, this point is point N. We defined the point of tendency of tangent AQ with this small circle, this point is point Q. Likewise, we defined the point of tendency of tangent AC with this big semicircle, this point is point H. And we defined the touching point of this small circle with this big semicircle, this point is point L. In the next step, we implemented the Pythagoras theorem of this right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle ABC, the hypotenuse is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. Repeat again. According to the Pythagoras theorem, in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. And AC square equals to AB square. AB is 6, therefore AB square is 6 square, that is 36, plus BC square. BC is 8, therefore BC square is 8 square, that is 64. So total AC square equals to 36 plus 64, that is 100. So AC square equals to 100. We took out of this equation and finally found out that the missing hypotenuse AC is equal to the square root of 100, that is 10. So AC equals to 10 units in its length. Here we can implement all two. According to all two, the lengths of two tangents from a common extent point to a circle are equal. We focus on this common extent point A. For this common extent point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And according to all two, they are equal to each other. This is to say AB equals to AH. Repeat again, according to all two, AB equals to AH. But AB is 6, so we can write here that AB is 6, and from this equation 6 equals to AB equals to AH, we derive that AH is also equals to 6 units in its length. This line segment AH is equals to 6 units in its length. What is the length of line segment HC? The length of line segment HC is equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. In the next step, we join points Q and H together by a straight line. Point Q is the center of this big semicircle. Point H is the point of the big semicircle itself. Therefore, QH is the radius of this big semicircle. We define the radius of this big semicircle as B. So QH equals to B. Here we can implement rule 1 because we have the radius QH that is equal to B. The radius QH is drawn to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever your radius is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Okay. So by doing this construction, we get the right triangle QHC. The right triangle QHC, we have this angle, angle C. Angle C belongs to the right triangle QHC. But angle C belongs also to the big right triangle ABC. Therefore, angle C is a common angle that belongs to both triangles. We define the size of this angle, angle A, as alpha. So in the right triangle in the right small triangle HQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first BC angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the right big triangle, triangle ABC. On the right big triangle, triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first BC angle must be equal to 90 degrees minus alpha. In the next step, we prove that the right big triangle, triangle ABC, is similar to this right small triangle, triangle HQC. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is the common angle that belongs to both triangles, so you can find out that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the triangles in the right big triangle, triangle ABC, are correspondingly equal to all the triangles of the right triangle, triangle HQC, therefore those two right triangles are similar to each other according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABC, or side HQ in the small right triangle HQC, equals to side BC in the big right triangle ABC, or side HC in the small right triangle HCQ. Repeat again. We will derive that side AB in the big right triangle ABC, or side HQ in the small right triangle HCQ, equals to side BC in the big right triangle ABC, or side HC in the small right triangle HCQ. AB is 6, HQ is B, this is the radius of the big semicircle is equal to B, BC is 8, and HC is 4. So in total, we can find out that 6 over B equals to 8 over 4. 8 over 4 is 2. So we can find out that 6 over B equals to 2. We multiply this equation by B and finally found out that 6 equals to 2B. Here we divided this equation by 2 and finally found out that the missing radius B equals to 6 minus 2, 6 over 2, that is 3. So the radius B of this big semicircle equals to 3 units in its length. Okay. So QH equals to 3 units in its length. Is the radius of this big semicircle. Likewise, QB is also the radius of this big semicircle, is equals to 3 units in its length. In the next step, we join points P and N together by a straight line. Point P is the center of this small circle, point Q is the point of the small circle itself, therefore Pn is the radius of this small circle. We define the radius of this small circle as A. A is the radius that we are looking for in this question. Here we can implement rule 1. Why? Because we have here the radius Pn is equal to 8, the radius Pn is 1 to point N, that is the point of tendency AB with this small circle. And whenever you have a radius that is 1 to the point of tendency, then tangent Pn will be perpendicular to the radius, tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the sum rule, all 1. Likewise, we join points P and K together by straight line. PK is the radius of this small circle that is equals to A. We have the radius PK that is 1 to point K, that is the point of tendency of tangent AC with this small circle. And whenever you have a radius that is 1 to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. The new rule is rule 15. I'll repeat quickly on rule 15. According to rule 15, from an external point of a circle, you will draw two tangents to that circle, then the angle that will be created between the two tangents is angle bisector must pass through the center of the circle. So in the drawing we have the circle and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. This angle, this is actually angle APB, was created by drawing the two tangents PA and PB. Now, according to this rule 15, the angle bisector of angle APB, the angle bisector of this angle must pass from point O, that is the center of this circle. Again, the angle bisector of an angle that was created by two tangents, that is angle APB, must pass from point O, that is the center of this circle. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, if we focus on this common external point, point A, from this common external point, point A, we have two tangents to this small circle, tangent AN and tangent AK. And according to rule 2, tangent AN and tangent AK. Those two tangent AN and AK created this angle, angle A. Again, this angle A was created by drawing the two tangent AN and AK to this small circle. Now, according to rule 15, the angle bisector of this angle A must pass from point P, that is the center of this small circle. Again, the angle bisector of this angle that was created by tangent AN and AK must pass from point P, that is the center of this small circle. If we define the size of this angle A as 2 theta, then the angle bisector PA bisect angle A into 2 halves. Each half equals to theta, of course. This is the first half, this is the second half. So if we're going to find out that the angle bisector of angle A passes through point P, that is the center of the small circle. Likewise, if we continue to focus on this common external point, point A, from this common external point, point A, we have two tangents to the big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. We have two tangents AB and AH to the big semicircle. By drawing the two tangents AB and AH, we created the same angle, angle A. Again, angle A was created by drawing tangent AB and tangent AH to this big semicircle. Now, the angle bisector of this angle A must pass from point Q, that is the center of this big semicircle. So if we found out that the angle bisector of angle A passes through point Q, that is the center of the big semicircle. And finally, it is very clear that the angle bisector of this angle A must pass through point A. So we can write down that the angle bisector of angle A passes also through point A. In conclusion, we found out that the angle bisector of this angle A passes through points A, P and Q. So here, the angle bisector of angle A passes through points A, P and Q. But the angle bisector of any angle is a straight line, and especially the angle bisector of this angle A must be a straight line. The angle bisector of angle A is a straight line. And we found out that the angle bisector of angle A passes through points A, P and Q. That is to say, all the 3 points A, P and Q are located on the same straight line. Okay, all the 3 points A, P and Q are located on the same straight line. And what is in which straight line all the 3 points A, P and Q are located? The straight line in the angle bisector of angle A. The straight line that all the 3 points A, P and Q are located here is the straight line of is the angle bisector of angle A. Because the angle bisector of angle A is a straight line, all the 3 points A, P and Q are located on the same straight line, that is the angle bisector of angle A. Okay, so all the 3 points A, P and Q are located on the same straight line. And the straight line is the angle bisector of angle A. Okay, so all the 3 points A, P and Q are located on the same straight line. Or in other words, you can also say that line segment APQ is one straight line. Again, line segment APQ is one straight line. And because of the fact that line segment APQ is one straight line, it means that this angle theta is a common angle that belongs to both triangles. It belongs to the small right triangle A and P, and this angle theta also belongs to the big right triangle ABQ. Okay, again, as we found out that angle theta is a common angle that belongs to both triangles, to the small right triangle A and P, and angle theta also belongs to the big right triangle ABQ. Okay, so in the next step we will focus on the big right triangle ABQ. The big right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the right small triangle A and P, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta, according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the big right triangle ABQ is similar to this small right triangle, triangle A and P. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, this is a common angle that belongs to both triangles, so we can write down that the angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually prove that all the three angles of the right big triangle, triangle ABQ, are correspondingly equal to all the three angles of the small right triangle, triangle A and P. Therefore, those two right triangles are similar to each other according to angle similarity rule. Okay, again, actually found out that the right big triangle ABQ is similar to the small right triangle A and P according to angle similarity rule. And for the fact that the right triangle ABQ is similar to this right small triangle A and P, we derive that the following relationship exists between their sides. We derive that side AB of the big right triangle ABQ, or side AN of the small right triangle NP, equals to side BQ of the big right triangle ABQ, or side NP of the small right triangle NP. Okay, again, We derive the side AB in the big right triangle ABQ over side AN on the small right triangle NP equals to side BQ of the big right triangle ABQ over side NP of the small right triangle NP. AB is 6 and AN is the missing side, so we leave it as it is. BQ is 3 and NP is 8. So in total we found out that AB over A, that 6 over AN equals to 3 over 8. Here we cross multiply this equation and we found out that AN equals to 3A. We found out that 6A equals to 3AN. Here we divided this equation by 3 and finally found out that the missing side AN equals to 6A over 3 is 2A. So this is the missing side. This is the missing side AN. This is equals to 2 units in its length. So AN equals to 2A, AB equals to 6, therefore this missing 9/7 NB must be equal to AB, that is 6, minus AN, that is 2A. So in total 9/7 NB equals to 6 minus 2A. In the next step we did the construction, that is to say from point P we draw perpendicular on BQ. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ, this point is point Z. By doing this construction, we did quadrilateral NP BZ. Inside quadrilateral NP BZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBZ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must meet its rectangle if not a square. So we relate to quadrilateral PBZ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle in PBZ, side NP must be equal to the opposite side BZ, but NP is 8, therefore BZ must be also equal to 8. Likewise, according to the same rule, in the same rectangle NPBZ, side NB must be equal to the opposite side PZ. But NB is 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. In the next step we found out the length of the missing 9/7 QZ. QZ equals to QB minus ZB. Again, QZ equals to QB minus ZB. QB is 3, ZB is 8, so in total QZ equals to 3 minus A. We have an external arch between this small circle and this big semicircle. That is to say, they touch each other externally at point N. And whenever you have an external arch between two circles, you can implement rule 10. So please quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the circles together must pass through their touching points. So here we have in the drawing two circles, and those two circles have an external arch between them at point B. That is to say, they touch each other externally at point P. The center of this small circle is at point M. The center of this big circle is at point O. And the straight line that connects the circles together is of course the straight line MO. So this straight line MO must pass through point P. That is the touching point. Again, the straight line MO must pass through point P. That is the touching point, or MPO is one straight line. Again, MPO is one straight line according to this rule, rule 10. We can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external arch between this small circle and this big semicircle. That is to say they touch each other externally at point L. The center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects the centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through point L, that is the touching point. Again, the straight line PQ must pass through point L, that is the touching point, or PLQ is one straight line. Again, PLQ is one straight line according to rule 10. If PLQ is one straight line, it means that PQ equals to PL plus LQ. Again, PQ equals to PL plus LQ. PL is A, PQ is 3, therefore in total PQ equals to A plus 3. In the next step, I commit the right triangle PZQ in a page and implement the Pythagoras with this right triangle PZQ. So actually, this is the right rectangle PZQ that the commit from the original drawing, commit to the Pythagoras theorem, this rectangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. PZ is A plus 3, or 3 plus 8, therefore PZ square is 3 plus A square, and this is equals to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square, plus ZQ square. ZQ is 3 minus 8, therefore ZQ square is 3 minus A square. So in conclusion, we found out that 3 plus A square equals to 6 minus 2A square, plus 3 minus A square. 3 plus A square equals to A square, to 3 square, that is 9 plus A square, plus 2 times 3 times 9, plus 2 times 3 times 8, that is 6A, and it is equals to 6 minus 2A square. 6 minus 2A square equals to 6 squared, that is 36, plus 2A squared, that is 4A square, minus 2 times 6, that is minus 12, times 2A, minus 2 times 6, that is minus 12, and minus 12 times 2A is minus 24A, plus 3 minus A square. 3 minus A square equals to 3 square, that is 9 plus A square, minus 2 times 3, this is minus 6 times A is minus 6A. So here we have 9 on both sides of the equation, so 9 get cancelled. We have also A square on both sides of the equation, so A square also get cancelled. So after cancelling those two expressions, this side of the equation we have only with 6A, the other side of the equation we have 36 plus 4A squared, minus 24A minus 6A is minus 30A. Okay, so in conclusion we found out that 6A in the side of the equation we have only with 6A, in the other side of the equation we have 36 plus 4A squared, and minus 24A minus 6A is minus 30A. Here we subtract the 6A from this equation. After we subtract the 6A in the side of the equation we have nothing, that is to say 0. On the other side of the equation we have 36 plus 4A squared, and minus 6A minus 38 is minus 36A. So in total we actually found out that 0 equals to 36 plus 4A squared minus 36A. Here we divided this equation by 4 and found out that 4A squared over 4 is A squared, and minus 36A over 4 is minus 9A, and 36 over 4 is 9. So in conclusion we actually found out that A squared minus 9A plus 9 equals to 0. So this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the formula. X equals to minus b plus minus 4 to b squared minus 4 times ac over 2a. In our specific quadratic equation, a squared minus 9a plus 9 equals to 0. The variable that we are looking for is a, so x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 9, and the coefficient c equals to 9. The only thing that is left to do is to put the data of our specific quadratic equation inside this general formula for x, and we find out the value of the rules of a, because x equals to a. So x equals to a, therefore a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a is 1, so minus 4 times 1 is minus 4, times c, that is 9, so minus 4 times 9 is minus 36. So inside the root we have only with 81 minus 36 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So we found out that a equals to 9 plus minus 81 minus 36 is 45 divided by 2. So a equals to 9 plus minus 4 to 45 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus 4 to 45 over 2. 9 plus 4 to 45 over 2 is greater than 3. So if we found out that the radius A of this small circle according to the first solution is greater than 3 units, but it is impossible that the radius A of this small circle will be greater than 3 units. Why? Because of the fact that the radius of the big semicircle equals to 3 units, and the big semicircle is definitely bigger than the small circle, and therefore the radius of the big semicircle that is equals to B must be greater than the radius of this small circle, or in other words, the radius of this small circle must be less than 3 units. But according to the first solution, the radius of the radius of the small circle is greater than 3 units. So therefore this solution is the correct solution. We can set the solution, and we're left only with the second solution that is possible for A. A is the radius of the small circle, so A according to the first solution equals to 9 1 square root of 45 over 2. 45 is 9 times 5, so we substitute 45 when 9 times 5 is inside the root, and we actually found out that A equals to 9 1 square root of 9 times 5 over 2. Square root of 9 is 3, so inside the root we have only 5 divided by 2. So according to the second solution, the radius of the this small circle, the radius A equals to either 9 or 3 times square root of 5 over 2 units in its length, or the radius A of this small circle equals to 1.146 units in its length. I repeat again, the radius of this small circle equals to either 9 minus 3 times square root of 5 over 2 units in its length, or in terms of numbers, the radius of this small circle A equals to 1.146 units. Okay, thank you very much.